Good morning, everyone. All right, thanks, Zach. So we get going. Number 54. Okay. So we're dealing with secant and tangent. And the idea is pretty much like the idea of sine and cosine. We're going to split off a term. Either we split up secant square or we split up secant tangent. And if really nothing works, we turn it into an integral of sine and cosine. Or we use some, as I said yesterday, a bit of our creativity. So let me look at number 54 and see what we need. 54. Okay, so that's a definite integral, so we have to take care of that. Okay. All right. Ideas. What would you do first? What will jump to your eyes when you see this integral? Just something should jump to you.
The x squared.
Yeah. Yes. And what else? X squared jumped, exactly.
X squared and x.
X squared and x should jump to you. Okay, which means that what should you do?
Would putting u to x squared and then taking the derivative, you get x or
Right.
2x.
Exactly. We start with a substitution. So we're going to take q to be x squared. I know that there is a sine cube, but before the sine cube, I really see this x squared and x. So we're going to start with a substitution. Sorry. And we're going to change limit. I mean, you don't have to change limit, as you guys know. We can leave that to the end. So it doesn't matter. That's a choice. If x is 0, my u would be a 0. And if x is the square root of pi over 2, my u would be pi over 2. And now I'm going to turn this whole thing into an integral in u. That's pi over 2 now. And this would be sine cube of u. And the dx would be a half du. So now I have a new integral. You can think of that as a whole new integral. U is my new variable, and my new limit are 0 and pi over 2. So now I have a whole really new integral. Now, do we know how to do that? Back to you. This is an integral in sine. It's not tangent and secant. And what do you want me to do? What do you do now?
Separate it into sine squared and sine.
Exactly. We're going to break it up. That power is odd. Whenever the power is odd, we break things up. So we're going to break it up. Du. And then what we're going to do? Keep going.
It's sine squared and sine, right? Not sine squared and cosine.
What? Repeat.
It'd be sine squared and sine.
Oh, my apology. Thanks. Okay, and then what do we do? Why did we split?
And we make it we make sine squared 1 minus cosine squared.
We make that. And what's the goal? Why do we do this?
So that we can then make u cosine or sine.
Yeah, but we're not going to call it u again, right? I'm not going to call u equal sine u. It doesn't really make sense. We're going to call it t. Okay, we're not going to use again the same u. So now we want this to be the derivative. So we're going to put u to be the cosine of u and make another substitution. Okay, I'm not going to call it u because it's very confusing. Then the dt will be minus sine u, and now we change limit. Remember, if we change limit, I don't go back to my original. If u is 0, u is 0, u is 0, the t is the cosine of 0, which is a 1. If u is pi over 2, the t is minus the cosine of pi over 2, which is a 0. So now I'll end up with a half times. The 0 went to 1, pi over 2 went to 0. Even though this is larger, you keep it like this. You don't really, and this is going to give me minus d. Okay.
Wouldn't the cosine 2u be cosine? Wouldn't it be t squared?
Yes, of course. Actually, does it matter at this stage?
Oh, okay.
You're right. I will change it immediately. But do you think it's the same thing?
Yeah, yeah.
It's really the same thing, absolutely. But you're right. I shouldn't have done this. But the end result will be the same, but it's my mistake. So finally, I'm getting equal to. Now I'm done. This is a t. One and 0. The value at the upper, it's 0, minus at the lower, I have 1. I have that. So finally, I'll end up with minus a half. 1 minus a third, that's a 2/3. It's going to give me 1/3. Okay. So let me look at your other problems while you guys see if you have any question about that. Oh. So that was a nice one. Now number 42 and 46. All right, 42 is the integral of the square root of tangent secant 4. Okay. All right, get going. What do you want to do? I'm listening. Even if you don't know basic answer, if you don't know anything, what is the term that bothers you? Square root of tangent. So even if you don't know anything, I have no idea how to deal with the square root of tangent. So even without any knowledge, as you're going to put u equal tangent, even if we haven't heard of that, because who want to deal with the square root of tangent? I don't know how to do that. So we're going to put u equal tangent x and go from there. Now, it means the du is secant square x dx. And now, as you know, we have everything has to be in terms of tangent. So we're going to split off the secant square term. So in this here, I'm going to first split off the secant square term. And we know we can do it and everything will work well because this power here is an even power. And then we're going to substitute everything. So tangent, I know it's going to become my square root of u, but this one is problematic. So it's going to be 1 secant square is 1 plus tangent square times secant square x dx. And now I am prepared to substitute. square root of u. 1 plus u squared, and this is being taken care of by the du. Now we've done a lot like those problems, so it's going to give me u to the half 1 plus u squared du. I will distribute.
I have a question. What does the secant squared x become? I can't
1
read
plus
that last
tangent.
part.
Oh, this one?
Yeah.
1 plus
This is-
tangent square.
Oh, okay.
Yeah, you
okay.
should. Yeah, this is. You should memorize those. The two things. First, sine square plus cosine square equal 1. Total memory, because you guys will use that. And as I said yesterday, divide across by cosine square. This will give you that 1 plus tangent square equal secant square. And from this one, you derive tangent square equals secant square minus 1. And from the first, you derive sine square is 1 minus cosine square, and cosine square is 1 minus sine square. Okay, these are the two trig identity that you will encounter. All right?
All right. Thank you.
Sure. Okay, so now, this will give me u to the power a half plus u to the power 3 half. So we're multiplying meaning adding the powers. And then it's a simple integration. This will give me 2/3 u to the power 3 half. And that will give me 1. We're going to add 1 2/5.
If you're adding the powers, wouldn't it be 5/2 and not 3/2?
Which one?
For the step above. U to the 1/2 times
This one.
u to the
This
squared.
one. Yeah. I just do mistake to make sure you're following me. All right, equal to 2/3 plus 2/7 end of the picture. All right, so we look at the last one and then we move on. Okay. So number 46. We have the following integral of times tangent cube. The secant minus 2 of, so I know it's really an ugly notation, but that's what we have to deal with. It's basically over secant square if you want. All right, again, ideas.
Make tangent the u because derivative of tangent is secant squared.
Mm-hmm. Okay, let me try that, see if it works. U equal, I'm slowing down because I want you to keep thinking. U equal tangent. The du is secant square, but the du is in the denominator. The secant square is in the denominator. Right? So how I'm going to pick it up? Are you with me? Okay, the student who picked up u to be tangent. Do you see what the problem is?
Yeah, I see that now.
You see it? Yeah, it's not
Mhm.
multiplied by secant square.
Yeah, it's 1 over secant squared.
Right. So we always try. So this is not working. Now I'm having another suggestion. Somebody's telling me so. This doesn't seem to work because, I mean, I don't know what to do here. So I'm gonna try u equals secant. Somebody is suggesting that. All right. If u is secant, the du is secant tangent. Okay. Do you think where this will do? Let's see if this will do. I'm gonna use a pencil so I can erase if it doesn't. All right, this will be taken care of. This will become u square. How about tangent cube? So what am I supposed to do?
You need to split the tangent so that you can make it secant
split.
squared minus 1, right?
Yeah. I'm really following along with you to see where I'm gonna get. So secant square x is not problematic. And the x.
I have a question.
I'm listening.
Shouldn't we have split the secant and tangent, like not split, but like take one from each away, so we can have the du of secant.
How? I don't make magic. I have to deal with what I have.
Oh, we can't take like we did yesterday. We can't take one away from each.
But this is in the denominator. I can take it all right, but I'm not going to get secant tangent. Do you follow what I said? I don't think so. Secant square is in the denominator. I can split. I don't have a secant square in the numerator. Watch what I have. I can split it down here, but how I'm going to pick up a secant tangent?
Oh, okay. Would it have worked if we had kept it in its like original form?
This form?
No, the one on top. On top of that. Right.
No. This is -2. It's not secant square. I think so, right? Am I wrong?
No, you're right. You're right.
No,
Okay.
no. There is nothing I can do. It has to go in the denominator. So I cannot do this. I cannot split it off. It's in the denominator.
The book separated to a secant and a tangent, and they just made the secant, they made that secant to -3 instead.
Well, how do you want me to do that? I'm not following verbatim.
They left it at the top and they separated out a secant x and a tangent x. And instead of that -2, they made that a -3.
How can I make that into a -3?
They multiplied the numerator and the denominator by secant x.
Oh, so that's what you're suggesting, right?
Yeah.
Okay, that's very smart. Very good. Okay, so let's see what your classmates are suggesting. They want me to do. We got here and we're actually stuck. Why are we stuck? So we're gonna do it 2 ways, okay? Why are we stuck at this stage? Because when the student picked u equals secant, the du is secant tangent. But secant tangent is nowhere in sight. Secant is in the denominator. It's really nowhere in sight for me. So what they are suggesting is the following. So this is, I'm gonna keep a secant square for now. So what they are suggesting is multiply numerator, denominator by secant. So they can bring this to the picture, which is actually absolutely correct. So they want me to do that. Secant square, I am not touching it, but they told me multiply by secant. So it's, as I said, that's creativity is getting here, and divide by secant. So multiply and divide. Can I do that? Of course, algebraically, it's correct. And why did they wanted me to do this? First, now I have this term. The denominator became secant cube. I can take care of that. Tangent secant dx. And the tangent square will become, as we said, this is the properties relating them. So tangent square is secant square minus 1. Okay. And now they are everything in terms of u. This became the du. So it's going to become integral of u square minus 1 over u to the power u du. And now this is equal to integral of u square over u to the power 3. So I'm going to split the numerator, which give me 1 over u minus 1 over u to the power 3. And now I proceed. I will get 1 over u minus u to the minus 3 du. So finally, it will give me ln of u minus 1 over minus 3 plus 1. Minus 3 plus 1 is minus 2. So this is going to give me u to the minus 3 plus 1 plus c. So finally, I will have ln of u, ln of tangent x, plus 1/2 1 over tangent square x plus c.
Isn't u secant?
Because, yes, of course, u is secant. I was looking at the first substitution. Over secant square x plus c. Okay. So it wasn't straightforward. It required a certain, basically, trick, if you want, to be able to do it.
I did a different way. I don't know if would that work if I just changed it to cosine and sine.
I would like to try this. I didn't. I would like to try it. I will try it with you. Okay? All right, we will try it, see how it works. Any questions about that? So I'm going to try the other one and see if it works, and then we proceed. So we will try what your classmate is suggesting. So in integration, there is a lot of trial and error, as you realize, which is make them more, fun to work with. So my issue was, this is my integral over secant square x dx. And another approach say, since it wasn't very straightforward, okay, let's write everything in terms of sine and cosine, which is, as I said yesterday, sometimes, it's nice to do. So if I write everything in terms of sine and cosine, tangent cube is going to become sine cube over cosine square. And this would be 1 over, over cosine cube, 1 over cosine square dx. Okay, and this is a square here. So if we use the property of fraction, it means I will have sine cube over cosine cube times cosine square dx. So finally, I will have basically sine cube over cosine x dx. And then how did you go from there?
I split the sine squared. I did the sine cube to sine squared and sine x.
Absolutely correct. So sine cube, and I think this is a little bit easier. I would have done it this way. I would have tried that. Yes.
And then
go ahead.
The
Go
sine
ahead.
squared becomes 1 minus cosine squared, and then do u substitution.
Right. X, and now I'm going to put u to be, I want this piece to be the du. So u is going to be the cosine, and the du is the sine x dx. Equal to, now I will have 1 minus u squared over u times the du. So do you guys see how it worked? So sometimes, you know, when you find it hard, just go to sine and cosine and hope for the best. I always say hope for the best because with integration, I am not sure our approach will work. We have to try other things. That's really part of the integration. So now finally, we're gonna split the numerator, which is gonna give me 1 over u minus a u du. And this will be equal to ln of u minus a half u squared plus c. And this is going to be equal to ln of cosine x minus a half cosine square x plus c. And even though the answers look a little bit different, but actually if you differentiate both of them, you will get exactly the integrand required. All right? Okay. Any questions? So we can do this problem 2 ways. The first way required creativity from your part. You guys, you know, said, okay, multiply, divide by secant. This was not a trivial way to do it. And this is, I think it's more straightforward, but we have to move to sine and cosine. Right. So today we're going to move on to, we still have 2 integration techniques we're going to learn. I'm going to start section 8.6, and then I'll go back. No, wait a second, how's this book divided? 8.5, and then I will go back to 8.4 because 8.5 is honestly more important than 8.4, and I want to do them in order of importance. So the way we're going to do it now is I'm not skipping section 8.4. I will go back to it. And 8.4 actually is going to use those again. But for now, I'm going to start section 8.5 because it's another extremely important integration techniques. So 8.5, partial fraction. All right, so I'm going to put 2 integrals in front of you, and I want to ask you which one is easy, which one is hard, and how to take care of the hard one. All right, so I'm going to put 2 integrals. X over x squared minus 4 dx, and 1 over, or let's see, 4 over x squared minus 4 dx. Okay, and my question to you is, which is easy, which is hard? I'm gonna call this one, I'm gonna call this 2.
One lends itself to substitution easier.
Right, one is easy. I can put the substitution. U equal, because the derivative of the denominator is really staring at you up to a constant. So I'm going to put u to be x squared minus 4. My du is the 2x dx. And then this would become a half integral of 1 over u du, which is going to give me a half ln of u. It means a half ln of x squared minus 4 plus c. What about the second one? What about the second one? If I put u equal x squared minus 4, the derivative is 2x dx. It's nowhere inside. I just put 4 because I felt like putting something. Okay, there is nowhere inside. So substitution will absolutely fail in this scenario. Okay, so here substitution fail. It's such a simple integral. You know, imagine you should be able to do it. So substitution fail. Because the derivative is nowhere inside. The denominator is nowhere inside. So the goal today, and not today and tomorrow, of course, probably the day after, for the next 3 days is, I mean, this one will be done today, is to actually learn how to integrate this type of function. But what do I mean by this type of function? I'm going to give a name to this integral. So to do that, we need a little bit of terminology, not a lot. So some terminology so I can describe the nature of this. So bit of terminology. Okay. First, when in math we say a monomial. A monomial. Monomial. Because I want to define polynomial. A monomial is a function or is an expression of the form or a function actually is a function of the form f of x equal a certain constant a times x to the power n, where n is an integer, a positive integer, and that's important. A positive integer, it means or n is 0. Okay, so a monomial is just a function that have very specific format. It's a times x to the n, where n is a positive integer or 0. So example of monomial. So suppose f of x equal 4 times x squared. So a is a constant, big deal, and a constant. Okay, so a is 4 and the power n is 2, which is a positive integer. So that's a monomial. Okay. Now, however, if I take f of x to be 4 times the square root of x, is this a monomial according to my definition? Yes or no?
No,
No, because what's the power of x here?
not positive.
No, that's not the
It's-
answer.
It's 1 over 2.
It's 1/2. And 1/2 is what? It's not an integer. It's not the positive. It's not an integer. Okay, I want an integer. Integers means 1, 2, 3, 4, 5. That's integer. A half is not an integer. So that's not a monomial. That's a typical monomial. Now, what's a polynomial? Polynomial is the sum of monomial. So a polynomial, so we have to know exactly what the word polynomial means. Poly, it means many. Polynomial is a sum of monomial. So polynomial are very specific type of functions. So example of a polynomial. So p of x, for example, let us say 5x4 plus 2x squared plus 4. That's a typical polynomial. And the degree of the polynomial is the highest power of x that shows up. So here the degree of this polynomial, that's the one, the word you know, I'm sure. The degree here is the highest power is 4. What's not a polynomial? So suppose I put p of x equal the square root of x squared plus 2. That's not a polynomial. So polynomials have very, very specific structure. Those are the easiest type of function we deal with. They have to have exactly this format. No square root in the picture at all. So they have to have the format sum of monomial. So sum of expression of the form 5x4, 2x squared, and so on and so forth. Now, what's a rational function? And that's really what we want in this particular chapter, in a section. So a rational function is basically the ratio, is the quotient of two polynomials. So, or is a function of the form. So a rational function is a function of the following form. F of x equal p of x over q of x, that's a rational function, where p and q are polynomial. Are polynomials. Okay, so a rational function, which is going to be our interest, is a function that has the form p over q, where both p and q are polynomials. Okay, and in this section 8.5, what we are going to learn actually is how to find the antiderivative of rational function. Very specific format. Function of the form p over q, where both p and q are polynomial. This is what we're going to learn in this section. So, for example, the one I started with, for example, when I took the integral of, if I take the function f of x equal x over x squared minus 4, that's a rational function. P of x, that's a polynomial of degree 1, and that's a polynomial of degree 2. That's rational, typical rational function. Well, integrating it was very easy, as you guys realize. Its antiderivative is easy because substitution worked. Okay. However, when I took the function f of x equal 4 over x squared minus 1, that's also a rational function. The degree of the numerator is 0, because you can think of this x to the power 0, degree is 0, and thus the degree is 2. But this is a bit harder to integrate. Okay, so our goal today is basically to deal with rational function, how to integrate all kinds of rational function. All right, we'll start, of course, with easy example. Let us say I can do that. So I'm going to a little bit focus on this. Forget about it. Let us say that we can do the following. We can rewrite. The word rewrite is important. 4 over x squared minus 4 as follow. Okay. So suppose this expression, 4 over x4 minus 4 by magic that we're going to learn, suppose I can rewrite it. And the word rewriting easy. Suppose I can rewrite it like this. Basically, sometimes we can decompose it like that. That should be plus 2. So suppose by magic, if you want, the magic that we're going to learn very soon, we can rewrite it like this. First, let me make sure, what do we mean by rewriting? Rewriting means that this expression and this expression are the same. We are just like kind of rewriting it. And how can I make sure that those expressions are the same? So we have to make sure that I'm not changing the expression. Notice one thing, that x squared minus 4 is x minus 2 times x plus 2. So those terms here are basically the factors of the denominator. So rewriting means that if I start with this expression, so rewriting means that they are the same. And I move backward. It means I find a common denominator, which is going to be that, and evaluate this expression. So that's x minus 2 minus x plus 2. I evaluate this expression. I will get x minus 2 minus x minus 2. So I think I flipped the sign here. I will change it. Divided by x squared minus 4, which is going to give me minus 4 over x squared minus 4. So I'm going to change the sign because I think I flipped them a little bit. So plus, I will get the plus 4. Okay, so rewriting, it means write this expression as sum of things, but they are the same. So that's what rewriting means. I'm not changing, I'm just making it a little bit simple. It's important to notice that here are the factors of that. Now, suppose I can do that. Will the problem become easy? Will integration become easy? So suppose I can do that. Then the antiderivative of this one will be equal to the antiderivative of that plus the antiderivative of this function. Okay, so being able to decompose it or to rewrite it in this format will make the integral much easier, because I transformed a hard one into two very simple integrals to deal with. So this will give me, if we do a little bit of substitution, this is going to give me ln of x plus 2 plus ln of x minus 1 plus c. Okay, so if I have this function and I can really split it or decompose it into sum of functions which are easier to integrate, and then it will be easy to find it. But the question for us today is how to do that. Today and tomorrow and the day after. How to decompose the function in this way so I can integrate, all right? So the question is how to decompose. So my big question is how to go backward. It means how to do that, not that, how to do that. So the question is how to decompose or rewrite in general, a rational function, but now I have to do the problem in generality, how to decompose a rational function into quote unquote simpler functions. So that's really our goal, how to do that, how to do this process. Okay, so there will be a lot of cases. It means how to decompose is going to be a lot of cases. So we're going to start in the first scenario, the big first case, and then another small case. So case one is going to be, suppose I have a function f of x equal p over q, that's my rational function, where the degree, so the first big case is going to be rational, where the degree of the numerator is less than the degree of the denominator. Okay, so to learn how to decompose, we are actually going to take lots of cases. So the first big case is, suppose we have a function, so we're going to decompose any rational function, where the degree of p is less than the degree of q. Okay. The first step to do, first step we're going to be doing, step one, the crucial step, we're going to factor out the denominator completely. Denominator completely. So at the beginning, I talk a lot, but then, so the first step, we're going to factor out the denominator as much as we can. And then the decomposition will depend on the factors that we're going to have. So we take the denominator, we factor it out, and the way we will decompose is going to depend on the type of factors the denominator will have. So situation number one, we're going to have the following scenario. So there will be a lot of cases, sorry about that, but so you can call it, so the step one, case one, or sub case one. I hate that word. Okay, suppose that the denominator has distinct means different, distinct, linear, and I will explain the word linear in a minute, linear factor only. Okay, so the first situation we're going to take on today, suppose the denominator has distinct linear factor only. Linear means factor of the form ax plus b. It means the power of x is 1. That's what linear factor means. Then we have quadratic, which is going to be the power of x is 2. That's we're going to call those quadratic factors. So today, only linear factor. So how do we write, if we have a rational function where the denominator satisfies this condition, how we will decompose? I will elaborate by examples. I will show you by example how the decomposition work instead of giving you the general format. It would be more complicated. The idea will be, suppose I have a function 3 over whatever, a rational function, x squared minus x minus 2. My goal at the end is to integrate, but now I'm not going to start to do that. How we decompose this? First, we totally factor out the denominator. And this denominator, that's a 2. So it's going to be 2 and the 1. That's a minus. Okay. Right. Then there is a theorem. Of course, we're not going to prove it, but we're going to accept it. It tells me the following. If you have a rational function, if the denominator could be split like this into distinct, it means different, linear factor, the theorem tells me that you should be able to find constant a and b so that this could be written as, so that's the factor and that's the second factor. So the theorem tells me that I should be able to find constant a and b so that this expression could be written like this, where a and b are constant that we're going to learn how to find them. Constant to be found. But the theorem guarantees that you should be able to do it. So it tells me in this scenario that this could be done. So for example, another example, suppose I have something like that, a rational function, and the denominator look like this. So I factored it and I get that. Okay, I have 3 factors, distinct, linear. The theorem tells me in this situation, you should be able to find 3 constants, a, b, and c, and rewrite this as, that's the first x, x minus 1, x plus 1. So it doesn't matter how many factors I have in the denominator, and as long as they are linear and they are distinct, a theorem in math tells me that you should be able to factor it, and where a, b, c are constant to be found.
I have a question.
I'm listening.
They have to be the same amount for the top and bottom, right? Like you can't have 4 on top or 3 on bottom.
I don't think I followed the question. Repeat.
So say it was, let's just say x, like instead of x right there on the bottom. If it was x minus 1, x plus 1, and x plus 2, would you be able to do it still since there's 4 on the bottom and 3 on top?
If you have 15 on the bottom, you can do it. It doesn't matter.
Oh, okay.
Okay, but I'm not going to write 15 of them. Okay, I'll just give you example for 2. It doesn't matter as long as they are distinct, as long as they are linear, as long as the degree of the numerator is less, then you can rewrite it this way. All right, so there are a lot of conditions. So the degree numerator has to be less. Those has to be linear and distinct. I mean, they are not the same. So I don't have another x here. Then we can decompose this way, regardless how many terms I have. Okay, I gave you 2 terms, 3 terms. I could have given you 4, but I want to show you how to find the constant. All right?
All right, thank you.
Very good. So now the question is how to find the constant. Once we know how to find them, we're done because we know how to integrate. Each one of those is a very simple integral to do. So the question is how to find the constant. Now, there are 2 ways to find them. I will emphasize one today, and then I will emphasize another one tomorrow. Okay, and I will not emphasize the one in the book. I will emphasize another one. So the question is how to find the constant a and b. How to find, sometimes you call them coefficients. So how to find the constant or the coefficients, a, b, c, etc. Excellent. All right, here's the trick. So I'm going to take the one I had here, 3 over x squared minus x minus 2, all right? And I'm gonna say, okay, I factored out the denominator. It's a 2, it's a 1, it's in x a plus and x minus. And I say, okay, math told me that I should be able to factor, to decompose. Okay, and how I do that? Okay, the way we're gonna decompose, we say, okay, like this. Mathematically, those should be equal for all x. So I'm going to multiply across. Basically, I want to get rid of that. So I'm going to multiply across by the common denominator. X plus 1 times x minus 2. Okay, we're going to multiply across by that. So if I multiply, so this I'm going to multiply it by x plus 1 times x minus 2. This will be multiplied by x plus 1 times x minus 2. Of course, across, otherwise, mathematically, it's not right. So each term is going to be multiplied across by this. I'm multiplying by the same term. This would give me 3 for the first. And this will give me x plus 1 simplify will give me x minus 2. And this would give me x minus 2 would give me x plus 1. We will be done in 2 minutes. Okay. Very good. Now we're going to think along the following line. We're going to say, I want A and B so that this expression, I want those two to be equal for all x's, because I want this to hold no matter what x is. So I want this to hold for all x. So I say, okay, if I want this to hold for all x, it should hold for x equal to 2. So I'm going to plug in x equal to in both sides, because that's really the logic we're going to go. I want them equal for all x, in particular x equal to 2. So I plug in x equal to 2. It's going to give me 3 equal a times 2 minus 2. And you will see why I picked 2, 2 plus 1. So this is going to give me 3 equal 0 plus 3b. b will be equal to 1. That's how I pick up my b. So it's very easy how to do that. Then my second piece is, I want my a. So by picking x equal to 2, I was able to get the b. So if I want to get the a, I say I'm going to plug in x to be equal to minus 1. Because if I plug in minus 1 here, this will go to 0, and I will pull up my a. This will give me 3 equal a times minus 1 minus 1. Sorry, minus 1 minus 2 plus b minus 1 plus 1. And this would give me 3 equal minus 3a plus 0. I solve for a equal minus 1. What does this tell me? This tells me that the expression 3 over x plus 1 times x minus 2, this expression is actually equal to minus 1 over x plus 1 plus plus 1, that's my b, over x minus 2. Okay, so I multiplied, I decompose, multiplied across by the common denominator, and plug in specific values of x here to help me to pick up my a and my b. Okay, now I'm done. Now the antiderivative is going to be equal to antiderivative of the first, which is going to be minus ln, plus the antiderivative of the second, which is going to be that, and of the problem. Okay, I'm sorry, I over time. So tomorrow, as you expect, we're going to work a lot along those lines, and we're going to consider more and more cases. So we will do more problems. I already have problem for you on MATLAB. You'll give them a try as usual. And we're going to do more problem along those lines and introduce more cases, just so that we can basically cover every rational function there is. Okay.